Hello, everybody. I'd like to thank the organizers for this opportunity to discuss our work on the dissipative spin hydrodynamics from microscopic approach, which is the kinetic theory. And if time allows, I would like to also discuss our ongoing project of analyzing the spin hydrodynamics from a macroscopic approach. I think it has been discussed a lot in this workshop that the discovery of lambda polarization in star has been sort of confirmed our understanding of the large total orbital angular momentum in having heavy ion collisions. And also it supports our understanding of the spin alignment effect with the vorticity. So for such measurement of the global lambda polarization, it has been shown that many different studies based on different models, including hydro or AMPT or other transport theories, can describe the value and the beam energy dependence of the polarization rate. So this sort of gives us a confidence that the global polarization of lambda can be well understood by assuming the global the equilibrium form of the spin degree of freedom, and it is independent of the detail of the model. So this is robust. However, when moving to the local spin polarization measured in heavy ion collisions, one expects sort of a robust disagreement, in particular in the sign of the polarization direction. So this drives our field to think more about the physics. So our understanding is more physics should be implemented to precisely describe the spin polarization rate, in particular the non-equilibrium correction and the feedback to the fluid. So we expect to construct a theory which correctly reflects the microscopic properties of the system. And this motivates our work. So let me mention that there are in principle two ways to construct the dissipative hydrodynamics. One way is, as Hongo just described, to construct the dissipative hydrodynamics from the macroscopic principles, from the conservation laws of the stress tensor and all the currents and the total angular momentum, and also implement the second law of thermodynamics. Entropy must the continuation equation of entropy must be non-negative. So in principle, such treatment should be general. It is robust to the microscopic details. For example, I would expect, if we focus on a system with only fermions or of a system of quark-gluon plasma, or even other situations, these principles should hold for all of them. But the sort of limitation of such treatment is we don't know the exact value of the transport coefficients, and this needs the input from microscopic interactions. So another way is to construct the hydrodynamic theory from a microscopic point of view. So in fact, the hydrodynamic quantities like currents and stress tensors and spin tensors could be they have microscopic definition. They could be constructed from microscopic quantities. So of course, the limitation or disadvantage for microscopic approach is that it relies on the microscopic details. One will have to specify the constituent of the system, the interaction detail of the system. However, after doing so, we would be able to obtain the exact value for the transport coefficients. Apart from that, as has been discussed a lot, in the macroscopic approach, the pseudo-gauge transformation might be some ambiguous. We don't know what is the most correct way to separate the total angular momentum into spin and orbital angular momentum. However, we can show that by this microscopic approach, the pseudo-gauge transformation is no longer an ambiguity in our framework. So I'd like to mention that last week in Kumar's talk, they also described a similar approach to construct the hydrodynamics from a microscopic approach by assuming the relaxation time approximation. So in this work, we are going to describe our approach to start from the chirokinetic theory and construct the hydrodynamic theory by taking the moment expansion. So if time allows, I would also like to briefly discuss our ongoing project that we find some extra terms in addition to the ones in the current literature for the macroscopic approach. So let me begin with the microscopic theory. So in this work, our goal is to construct the macroscopic theory for the hydrodynamic quantities from the microscopic distribution functions, which includes the spin degrees of freedom. Also, in this work, we aim to implement the vortical effect and the non-equilibrium correlations to both the microscopic and the macroscopic part in a consistent way. By doing so, we will be able to derive the equation of motion for these macroscopic quantities in a way which is consistent with the microscopic theory. Also, I would like to highlight that by doing so, the distribution function for hadrons at freeze out, in particular, the spin polarization rate shall be independent of the pseudo-gauge transformation. So to get the microscopic distribution of the fermions, I have to mention that in our work, we focus on the fermions, in particular, the massless fermions. So to describe the microscopic distribution function for fermions with implementing the spin degree of freedom, the correct way is to consider the Wigner function, which is a 4x4 matrix. So it is the Fourier transformation of a two-point correlation of the fermion field. This is a 4x4 matrix, and one can decompose this matrix into the Clifford basis. It contains scalar, pseudo-scalar, vector, axial vector, and tensor part. And the hydrodynamic quantities could be constructed from these Clifford components, especially the vector and axial vector part. So this gives us the link between the microscopic distribution function and the macroscopic hydrodynamic quantities. And then we need to understand the equation of motion for the microscopic distribution function, which can be given by the direct equation. For example, this is how the distribution, the equation of motion for the Wigner function looks like for freed fermions. So this is derived from the Dirac equation, and it is, I mean, if we remember that W is a 4x4 matrix, this equation of motion is a coupled equation for all the different Clifford components. And it's sort of hard to solve. And in this work, as a first step, we take a simplified version, which is the massless limit. So in this limit, one can see that the equation of motion for the Clifford components highly decoupled, especially for the vector and axial vector parts we are interested in. They only couple to each other, and the rest are they are independent to the rest. So as has been discovered in many previous work, in this case, one can have solution of the chirokinetic equation up to the first order of H bar. So one can construct the vector and axial vector currents from effective distribution function and obtain the equation of motion, which is the chirokinetic equation for this effective distribution function. In particular, I wanted to emphasize that by doing so, we include the quantum corrections or the vortical corrections to both the currents and the equation of motion for the distribution function in a consistent way. So with this chirokinetic equation, we can move on to get some information about the system. For example, starting from this chirokinetic equation, one can derive the equilibrium, the thermal equilibrium distribution under this interaction. So we can see that in thermal equilibrium, we find the vortical effect, the quantum corrections to the equilibrium distribution. And from this equilibrium distribution, we can further construct the equilibrium limit for the currents and stress tensor. So this is how it looks like. In the ideal limit, we already see that the vortical effect is included as the widely discussed chiral vortical currents for both right-handed and left-handed currents. It contains the so-called chiral vortical effect, and also the temperature square term here reflects the spin alignment effect. And apart from the generally discussed chiral vortical currents, you can also see that the quantum correction, the vortical correction, has non-trivial feedback to the medium by including these extra terms in the stress tensor. So far, we have seen that the vortical effect has been consistently implemented in from both the microscopic point of view and to construct the macroscopic quantities. Now, we move on to include the non-equilibrium corrections also in a consistent way and obtain the equation of motion for these non-equilibrium quantities. So we take the moment expansion formalism to sort of assume the form of non-equilibrium corrections on top of the equilibrium distribution. So here, lambda are the sort of standard 40-moment polynomials. They are polynomials of the energy in the fluid co-moving frame. And nu and pi mu nu are the dissipative quantities. And they are actually the dissipative quantities that show up in the definition of current J mu, current J mu and stress tensor T mu nu. So such dissipative quantities could be reconstructed from the as the momentum integral of such of equilibrium distribution function. So with this reconstruction, as well as the chirokinetic equation, which is the equation of motion for the microscopic distribution function, we can move on to obtain the equation of motion for the dissipative quantities. So after some simplification, we eventually obtain the equation of motion, which are the relaxation equations for such dissipative quantities, like pi mu nu and the nu alpha, which is the dissipative current. So they are relaxed to the Navier-Stokes limit by taking the relaxation time relaxation time correction. And for the dissipative currents, they couple not only themselves, but also, the right-handed current is coupled to the left-handed currents. So this is, in some sense, the has non-trivial spin alignment effect. And there are, of course, other effects which show up as second-order terms. So I'd like to mention that the tau here are the relaxation time here, tau, and the mixing term are computed from the integral of the collision terms. They reflect the microscopic properties of the system. And for completeness, I would like to show the complete expression for current and stress tensor, which contains the normal viscous hydro terms, the ideal term, the viscous correction here, and similarly here. It also contains the chiral-vortical effect in equilibrium, which are underlined with red lines. So they are comparable to the previous expectation of vortical effects in equilibrium. And also it contains other terms, which are the viscous corrections related to the vortical terms. So this gives us a complete theory to deal with viscous hydrodynamics with spin degree of freedom. So far, we have obtained the we have included the non-equilibrium correction to the macroscopic quantities and obtained their equation of motion. So I would like to highlight that such theory gives us an definite idea of the distribution function for hadrons at freeze-out, in particular the polarization rate. And this is independent of the pseudo-gauge transformation. The idea, the reason is, in this work, we really construct the macroscopic quantities from a microscopic way. And such microscopic distribution function F, it gives us a concrete idea of the distribution function for hadrons at freeze-out. For example, if we focus on the polarization tensor, the polarization rate, sorry about the typo here. So one can construct this vector from the microscopic distribution, the Wigner function. And by implementing the distribution function with viscous corrections shown previously in a few slides back, we could obtain the exact formula for the spin vector by implementing the viscous corrections. So this is the expression we obtained eventually. So if we focus on the terms in black color only, we could reproduce the existing results, for example, in this review. And then if we include the, because we include the axial charge chemical potential in this system, we also see the axial charge chemical potential has non-trivial consequence to the spin vector, which is well expected. And on top of that, we find the viscous corrections to the spin polarization that freeze out as blue terms here. So let me mention that if we try to, modify the definition of T mu nu and spin current in the macroscopic point of view, that's fine. As has been discussed, in principle, such a pseudo-gauge transformation does not influence the evolution of the quantities like velocity and temperature and etc. And also because this theory is constructed from a macroscopic distribution, from the macroscopic distribution functions, we have concrete idea of the exact form of the polarization vector. So the pseudo-gauge transformation does not influence the microscopic distribution function. That's why such theory have concrete idea on how the polarization is supposed to be. So then let me move on to sort of discuss our ongoing progress to construct the dissipative hydrodynamics from a macroscopic point of view. So as emphasized before, the advantage of such a macroscopic treatment is that it is general. It does not depend on the microscopic detail of the system. And as has been introduced very nicely by Hongo, in their work, they have already constructed the first order viscous spin hydrodynamics from the macroscopic principles of conservation laws and second law of thermodynamics. And then it will be interesting to compare these results. So I think I could sort of skip the details as it has been nicely explained. So the basic idea is to write down the conservation laws of energy momentum and the conserved charges, including all flavors and including both vector and axial charges, as well as the conservation of total angular momentum. Then we can combine these conservation equations together. And by taking into account the equation of state, the thermodynamic relations between these quantities, one would be able to obtain the entropy production or the continuity equation for the entropy. So this is what one can obtain as the production equation of the entropy. So I would like to highlight the difference. In this work, we take the thermal vorticity as the spin chemical potential. The reason is we think the equation of state is actually the relation for thermodynamic quantities. So such quantities must be corresponding to the global equilibrium. So we take the global equilibrium quantities, which is the thermal vorticity for the spin chemical potential. So as a consequence, we can see that in this production equation of the entropy current, it contains the symmetric part of T mu nu. It contains the heat current and the charge current, and also the spin part, but it does not constrain the anti-symmetric part of T mu nu. This actually leaves some room for the pseudo gauge transformation. And I would like to mention that taking this scenario, taking the thermal vorticity as the chemical potential, the spin chemical potential, one could actually avoid the inequivalence of pseudo gauge transformation, which is discussed in the recently posted paper by Fukushima and Poole. So this is sort of our starting point. And from this starting point, we get the production of the entropy, the production equation of the entropy current. And I mean, as the sort of standard procedure in Landa's textbook, the trick to explain, to respect the second law of thermodynamics is that we explained every term on the right-hand side as the quadratic term. So taking this idea, one can see that, for example, the first term must be a positive definite quadratic term. Then we expect that the bulk viscosity must be some quantity proportional to the expansion rate theta. And similarly, we can explain every term as the positive definite quadratic term. Then the natural question is whether this explanation, from this explanation, whether the terms we find are complete or not. The reason why I'm asking is it has been shown by Thorne and Shurovka that the chiral vertical and chiral magnetic currents could be introduced without violating the conservation and production laws. So it means that it would be worth to investigate whether one could include, say, the vertical terms in such quantities. And our answer is yes. For example, if we modified the formula of the entropy production equation and explanation or ansatz of the entropy current by adding some vertical related terms. But we also, of course, we have to make sure that on both the left-hand side and the right-hand side, such new terms, they are colored in red, should cancel with each other, which means we have included equal balancing or equal new terms on the left-hand side and right-hand side in this equality. If one can do so, we could include new terms, extra terms related to the vertical, the vorticity vector. In the definition of these currents, in the heat currents and the Q, which is related to the antisymmetric part of this the stress tensor. So these C's are coefficients, and they are not known yet, but they have to follow the balancing equation of these new terms. These are the constraint equations for the coefficients. So after some straightforward simplification, one can find this constraint equation will lead to a few constraints of these coefficients. For example, the combination of these coefficients must be independent of temperature. And regarding the chemical potential dependence, we find the constraint equation like this. And let me mention that it has been checked that these constraint equations does not completely fix the coefficients of these coefficients C, S, and etc. So these coefficients in this approach, there are some unconstrained degree. There are some unconstrained degrees of freedoms, and such extra degrees of freedoms shall be or can be determined by the microscopic theories, like what we discussed previously from Kinetic theory. And I also would like to highlight that such new terms, they are non-dissipative. To see this, we can follow the idea from Kaziev and Yi. On one hand, mathematically speaking, if we look at the entropy production equation, including such new terms does not bring extra quadratic terms in the entropy production equation. They do not lead to extra production of entropy. And to see this in a more sort of physical way, physical point of view, one can examine the parity, the parity property under time reversal transformation. We can find these coefficients are T-even. Where other coefficients like the transport coefficient sigma and shear viscosity, bulk viscosity, they are all T-odd. So being T-even, it means such coefficients, C coefficients, they couldn't be explained as transport coefficient like the diffusion equations. So this is sort of another physical point of view to see that such coefficients, such new terms are non-dissipative. So being non-dissipative, it means this vertical effect, they can exist even in the ideal limit. Although the vorticity correction, omega, is of first order in gradient expansion. This sort of remind myself that one should be careful about expanding the hydrodynamic theories in terms of gradient expansion, because gradient expansion is not necessarily the best way to expand the spin hydrodynamic theory. So with this, let me summarize my talk. So in this talk, we first construct the viscous spin hydrodynamics from the Kinetic theory by taking the moment expansion formalism. So in our first step, we focus on the massless the system of massless fermions. And our theory accounts for the non-equilibrium correction to spin polarization and the back reaction for the upward motion of the fluid. And then in our attempts of the deriving the viscous spin hydro from a macroscopic point of view, we find extra CV-like terms could be introduced in the macroscopic solution, where the unconstrained coefficients should be and can be determined by the macroscopic theories. So we are currently working on extending the macroscopic approach to up to the second order. I mean, in relaxation form, and we are also interested in constructing a more realistic spin hydrodynamics from the quantum kinetic theory for massive particles. And that's all for my talk today. And I will appreciate your comments and questions. Thanks.
Thank you, Shuzhe, for the very interesting talk. Okay, let's take the questions. First, Enrico, please.
Hi, could you please go to slide 12?
Sure. Here we are.
Yeah, so your point is the opposite that I just said, right? So you say that the expectation value, so the distribution function doesn't depend on the pseudo gauge, but I just showed you that the expectation value away from global equilibrium actually depends. So probably.
So I mean, my understanding is because here in this theory, we are not trying to construct the polarization. I mean, the polarization at hadron level from the macroscopic quantities. Instead, we reconstruct this quantity from a microscopic point of view. So from the microscopic point of view, I don't think the pseudo gauge transformation would influence the distribution function.
But still you need to make some thermal average. So still you need some density operator. So I think that in the end of the day, you need to calculate expectation value as well, even though you start from microscopic. But and also, what do I see exactly in your microscopic formulation, the orbital to spin angular momentum conversion? Where do I see that?
That's a very good question. So here, the OAM to spin conversion is not that explicit in this framework. So in principle, it is embedded in the collision term. So
in the which collision term is that?
Let me see. So in the collision term, in principle, one would be possible to find collisions that flips the helicity or the chirality of the particle. So this would bring non-conservation of spin.
But what do I see that I mean, there should be some balance in the end between orbital and spin, but I didn't see any. I don't know. Maybe.
I mean, I think this is a good question. To be honest, I haven't checked this in a great detail, but yeah, it will be interesting to see.
Okay. Thank you.
Thank you.
Next, Dylan.
Yes. Okay. Thanks for the talk. So, sorry, I'm a little bit distracted. So, can you go to the I don't know the slice number. The slice with these modifications is of the currents is with this vorticity and viscosity. Can you not viscosity stress? Yeah. Now this one. There should be some a slice with current, right? Oh,
do you mean this one?
probably in the next one with further the non-equilibrium correction.
Oh, I see.
Yeah.
This is what you mean, right?
Yes, that's right.
Yes.
Thank you. So I wonder, I mean, so I don't know whether you know that I and Yoshimasa wrote papers about these shear corrections couples to the vorticities is also from the chirokinetic theory. I want to understand what's actually the differences between our results and yours. So here, did you also, for example, for the last turn for this current, right? You also have this pi mu lambda couples to omega lambda, right?
This one, yes.
Yeah. So is this the same ones as we found in the paper? I wonder. So these are the second orders correction, right? In terms of gradient, right?
Yes, that's right.
So have you checked the coefficients are the same? Or?
I'm sorry, but I do know some of your literatures, but probably I didn't pay attention to the reference you just described. But I'll do so. I will make the comparison.
Okay, I see. Okay, so yeah, because we also have this term, so I wonder, yeah, whether, and I'm not sure whether we also derive other terms you have. Perhaps you can make a comparison because we also use the realization time approximation in the framework of chirokinetic theory. So in principle, it should be the same, at least for current. We didn't calculate the energy momentum tensor. So, but in principle, you can make a comparison for current.
Now I sort of remember. You're saying that your derivation is based on relaxation time approximation. Is that correct?
Right. So you are not doing relaxation time approximation?
No, actually, this is we use the sort of 14 moment expansion. So this might be different from the relaxation time approximation.
But how this depends on couplings? So the coefficient does not depends on couplings. What? I'm kind of confused. Maybe it's too technical, so maybe we can discuss later and let others.
Yes, sure. And I will make thank you for bringing this. I'll make a full, more detailed.
You can continue the discussion in the roundtable discussion.
Okay. Thanks.
So next, Francesco.
Yes. So I have maybe first a comment on what Enrico said. That
yes.
That if you go to slide number 6, perhaps no, maybe sorry, I made a mistake. Maybe it's the next one. Okay, now you can leave that. Okay. So in other words, when you define a Wigner function or a distribution function.
Yes.
Yeah. So in the first place, you need a density operator.
Right.
Okay? And the point by Enrico was that a local equilibrium. No, I'm not talking about global. So it's very important to stress the difference between local and global. But the local equilibrium, it apparently depends on the pseudo gauge transformation, the density operator, and therefore, a fortiori, the Wigner function or the distribution function can depend on the pseudo gauge transformation. This reflects in the form. So maybe if you go to slide number 8, in the form of the thermal equilibrium distribution. So at global equilibrium, it will not depend on the pseudo gauge transformation, but local equilibrium it will. And you may have in principle spin potential instead of thermal vorticity. So this is what Enrico stressed. So the expression of polarization does not depend on the pseudo gauge transformation, but its value does or can. this is the say if I reinforce his point, and then I then I have a okay. No, please. So if you want to answer
And
this point.
I mean, I just wanted to say now, thanks for your explanation. I think I understand better what the point is, and I need to think more about it. Thanks.
And then I have a suggestion about, so your expression of the polarization is very interesting, because so the one in slide I don't remember with the distributed correction. So this one, yeah, yes. I think this is very interesting, and it includes the same expression that Matteo Buzzegoli showed last Thursday, I guess. So with dependent chemical polarization, very interesting. But also you also have viscous corrections.
Yes.
So
yes.
I think this is very interesting, phenomenologically.
Yes, I would say so. Yes.
Yeah, and then I have a suggestion is the following: that in order to calculate the entropy current, so in order to include, and this perhaps goes to the point made by, I don't know, that when you have equilibrium with so in this case equilibrium with rotation, no, I mean the point you made, so that the equilibrium with rotation, the gradient expansion is not necessarily the best method. And,
yes.
And I would like to advertise a paper that Davide Rindori and I published last year about how to calculate entropy current in the general, say in the most general way from the local equilibrium density operator, and because I think this is applicable in this case. So in order to derive the formally exact expression of entropy current at local equilibrium, including the say when you have vorticity or things like those, or axial chemical potential and so on. And this is a paper by Davide Rindori and myself published last year.
Thank you for the reference, and I'll take a very close look at it. Thanks.
Thank you.
Yeah, next, Nora.
Yes, so my question is actually also connected to what Enrico asked and also what Francesco just did. So this form of this S mu, did you prove that this is independent of the pseudo gauge, so that also your coefficients are independent of the pseudo gauge?
Sorry, could you repeat the question?
Yes, so you said that this S mu, but what you show in the slide is independent of pseudo gauge, right? But did you try to do the same calculation with a different pseudo gauge, and did you check that all the coefficients are the same?
That's a good question. So I mean as long as the macroscopic quantities like T mu nu has been constructed, then the formula of the distribution function, the microscopic distribution function f, is independent of the pseudo gauge transformation I apply to the macroscopic, the hydrodynamic quantities. But since it has been mentioned that the pseudo gauge transformation might influence the definition of these quantities, then I'll need to think about it.
Okay. And also in the second part of the talk, you also used the dominant vorticity, right, instead of the spin potential. So when you construct the entropy.
Yes, right.
So I didn't understand. So if you have this as dominant vorticity, does not depend on pseudo gauge, but if you make this independent of dominant vorticity, it does.
So I mean, again, the pseudo gauge transformation I'm thinking of is, it applies only to the hydrodynamic quantities like T mu nu and spin current. So in that sense, oh, that's a good question. Whether the pseudo gauge transformation influence the definition of thermal vorticity. I haven't think of this before. Yeah, I'll need to think about it.
Okay, thank you.
Thanks. Thank you.
Next, Oleg.
I actually have a question also concerning the slide number 12. The same.
Yes.
Yes, just the expression for polarization seems to be quite similar to the expression we are using in the exploring the axial vertical effect, and which was actually in the one part of Yuri Ivanov talk in the first day. Except we calculate, well, we choose the specific frame corresponding to axial charge, the specific surface and frame corresponding to axial charge, to the zero component of the current. Yes. And also we calculated for quarks, not for hadrons. So maybe just also implementing some kind of quark-hadron duality in terms of axial charge. So this is just a comment.
Thanks.
Yeah, okay. Yeah, I think we can close this session here.